Hello everyone. Today I'm going to introduce you to my favorite integration technique, and alongside that I'm going to derive Ramanujan's master theorem, which is probably why you clicked on this. And also something else, Glaisher's master theorem, which anticipated Ramanujan's, which is it's nearly as powerful, if not more powerful. But we'll cross that bridge when we come to it. So, how would you even begin to conceptualize a master theorem of such power and grandeur? How would you think about creating it? Take a close look at the series inside of the master theorem. This is it, by the way. It's a terrible introduction, but so just cover up this f of k right here. Cover up that. What does that sum look like? Like e to the minus x, right? So we're going to need an integral from 0 to infinity, improper integral, of x to the s minus 1 and e to the minus x in it. So we're going to take that integral. So let's take this integral from 0 to infinity, x to the s minus 1, e to the minus x dx. And now we're going to do a substitution. We're going to let x equal a new variable times a new dummy variable, u. So dx is going to subsequently equal a du. And is that right? Yep, that is right. Then that's going to provide the transformation a to the s times the integral from 0 to infinity. Bounds are the same, because you're just multiplying by a. That'll still be 0 to infinity. Of u to the s minus 1 times e to the minus a u du. Okay, so if you look at this, if you look at our initial integral, just look at it. That's actually the definition of the gamma function, which is an extension of the factorial, but to fractional powers with this integral form. So, okay, now we're going to express this integral as a series. So we'll have integral from 0 to infinity. Oh, a to the s at the front, u to the s minus 1. And so to get this series right here, we're going to have to express the exponential as a series. It's a Taylor series. So k equals 0 to infinity. You have minus a, well, that's not a minus sign, minus a u to the k over k factorial du. Remember, this equals gamma of s. Okay. Divide both sides of the equation by a to the s. You get the integral from 0 to infinity, u to the s minus 1. So sum as k equals 0 to infinity. And we have minus a u to the k. K factorial du equals a to the minus s gamma of s. All right, now we're going to let a equal to a new operator. A is going to equal e. What's big E? It's very peculiar, but big E is actually e to the derivative. So it's a Michael Penn, actually, he posted a video about this roughly, I think, a month ago now, so you should definitely check that out if you're interested in this. And this is a very intriguing, beguiling topic, to me at least. But the main property of this big E operator is that e to the x times f of a equals f of a plus x. This is the fundamental theorem of big E. It's not copyrighted. It's not a trademark, but it's okay. Now, so But we need to make it so we have an arbitrary function. So we're going to multiply both sides of the equation by an arbitrary function. So we're going to get f of 0 times the integral from 0 to infinity, u to the s minus 1 times the series as k equals 0 to infinity, minus u to the k. Now that's not a anymore, that's big E to the k, over k factorial du equals e to the minus s times f of s, times f of 0 times gamma of s. Okay, now use the fundamental theorem of E, not trademarked. We get gamma of s times f of minus s. It should look familiar, actually. Okay, so because this is a constant right now, f of a single value, we can shove f inside of the integral and then inside the series, and then put it right up next to its friend, big E over there. So, and just get right in here. F of 0. Now, combine the two, and you get f of k. That's it. That's actually how you derive Ramanujan's master theorem. Here, I'm going to rewrite this gamma. So, that's how you derive Ramanujan's master theorem. Okay, now this next master theorem is pretty esoteric. I actually haven't seen it anywhere on YouTube. I guess I haven't gone searching for it either, so. Okay, but anyway, this is called a Glaisher's master theorem, which sort of anticipated Ramanujan's, and it has this nice factor 1 over x squared plus 1, which is, well, usually those integrals are pretty nice to deal with. So, well, not really nice to deal with. They have nice results, rather, so. Okay, so to derive this, we're going to do the same thing. However, we're going to, okay, think of a function. Just ignore this f of k right here. Think of a function that has an alternating even power series. Just think about that for a second. Yeah, just forget this f of k. Forget him for now. If you said cosine, you'd be very, very correct. So the power series for a cosine. You get cosine of x equals the sum as k equals 0 to infinity, minus 1 to the k, times x to the 2k over 2k factorial. Now, don't worry about this 2k factorial in the denominator, because that we can just put that inside of our arbitrary function in the end. So remember this. So now we're going to need a constant. So we're actually here. Let's form an integral real quick. 0 to infinity. We need the cosine divided by x squared plus 1. But we're going to need a constant to convert into big E later on. So we're going to let that equal a. It's going to be our constant. And now, this is actually going to be equal to pi over 2 times e to the minus a. That can be derived using complex analysis, some other techniques. So now represent the cosine function as a series. When you get the integral from 0 to infinity, 1 over x squared plus 1 times the sum is k equals 0 to infinity. You're going to have minus 1 to the k times ax to the k, to the 2k, actually, over 2k factorial dx equals pi over 2 times e to the minus a. All right. Now, we're going to want to have this, we're going to want big E to regard f of k, not f of 2k. See, if we were to multiply both okay, if we were to multiply both sides of the equation right now, and a were to be equal to big E, then what we would get is f of 2k. So, and because of that, we're going to let b equal a squared. So then a equals square root b. The integral from 0 to infinity. Okay, yep, you can see this. 1 over x squared plus 1 times the same series. K equals 0 to infinity. Minus 1 to the k times x to the 2k. But now it's b to the k over 2k factorial dx equals pi over 2 times e to the minus b, or e to the minus root b. E to the minus root b. Now we're going to let b is going to be our e. That's going to turn to our big E. Then we're going to multiply both sides of the equation by a new arbitrary function of 0. Now applying these transformations should yield the following equation. To go from 0 to infinity, you have 1 over x squared plus 1. The sum as k equals 0 to infinity. Well, this is f of 0 times this. Minus 1 to the k times x to the 2k times big E to the k over 2k factorial dx equals pi over 2 times e to the minus root b, right? Or e to the minus root e times f of 0. Okay, so we did this last time. You know the procedure. Put the f of 0 inside the integral and right inside the sum. Yep, and put the power inside of the f, and then you get f of k. However, now on the right side of the equation, we have a function of big E. So how would we get our f of 0 to be with our friend big E? That's, I mean, they can't be together right now. They're separated by a function. However, once again, you can expand it as a series. So this would go pi over 2 times f of 0. Now the Taylor series expansion for E would be minus 1 to the k times big E to the k over 2, this is square root, divided by k factorial. Now put the f of 0 inside of that, inside of the sum, and you get f of k over 2. And now, final step, just to really generalize it more so, would be to let a new function, new arbitrary function, g of k equal to f of k over 2 over k factorial, right? And so then f of k, you just let k equal 2k, then you get f of k over 2k factorial, which is right up here. So then, finally, you get the sum as from 0, well, we get the integral from 0 to infinity, x squared 1 over x squared plus 1 times the sum, k equals 0 to infinity, minus 1 to the k, x to the 2k. That's our g of k now. Just put g of k dx equals pi over 2 times the series, it's k equals 0 to infinity. We have minus 1 to the k That's going to be our g of k now. And that is it. This is Glaisher's master theorem. Okay, so you can actually, you can make more master theorems off of this idea, and that's sort of turned to a bit of an integration technique for me, and I'll actually introduce an example of that in the next video. So, all right, have a flammable day.